Slido was working through the tutorials, and the answer is no, because you need to talk to your tutors at that time, and that cannot really be anonymous, right? Like, it doesn't make sense that people don't really help you and know that there is a problem. I mean, seriously, do it just, oh, hi, we have a guest. Hello. Tomorrow, I'm going to tell about experiment that we did with cats. So probably keep it outside, right? No, don't keep it outside now, tomorrow, because he might be scared. See, one cat's anesthetized with electrodes in his head and stuff like that. Anyway, yeah, so talk to your tutors. Don't be afraid to just ask questions. Seriously, there are no stupid questions in general. The other thing is use Slido, please, to ask questions if you during lectures and so on, because it's really a good method. If you don't feel like you want to do it open with everyone, yeah, and that is fine. All right. So let's start by asking if there is any question about the part before, if you had time to digest what I was telling you about, and where are we going with this and stuff like that. Do you have any question that you want to ask me about before we move to talk about plasticity? No question about the motifs. Good. So let's see what we're going to do this afternoon. You'll be pro at that. Okay, so for the next part, I'm gonna take it very, very philosophical. So the first question that I want to focus on is, why do we have a brain? And here I want to hear your voice. So give me some answer. Why do you think we have a brain? What is the power of our brain? What is the main job of our brain? Yes, David?
To learn.
Yeah, that's a very good job. But it's not the only one. Like, I mean, to learn, you need to have some substrates to work on.
Yeah, I think example of Phineas Gage, it is the seed of our consciousness and personality.
That's another very good question. And philosophically, this has been tackled in a very precise neuroscience way. If you read about John Locke, he was telling us, going back to what David was saying, that the ability of our brain to create memories is what actually allows to be the same person day by day. You are the same person today that you were yesterday because you have a link of memories that connects you. If you were not able to create a link of memories, you couldn't be the same person from one day to the next. This is something that Christopher Nolan explored with the movie Memento, for example, right? The guy that was tattooing stuff on his body. If you haven't watched it, you should watch it. I mean, it's old, I know, but it's a great movie. Any other suggestion, idea?
Yeah, sorry.
Yeah, details.
For the sense. So if you take them more in general, all started with the eyes, with the nose, motoric sensors. You need something to coordinate that.
Perception. Yes, absolutely. You need to create a mental picture of the world around you, right? A substrate in the language of the brain that we know from yesterday's electricity, on which you can work on. If you have no image, you cannot really attach any meaning to it. Yeah, absolutely.
Yeah, and what I want to say, it also coordinates the unconscious processes that keep the body alive by itself, then sends the impulse that causes to breathe, it causes our muscles to move, and so on and so forth.
Yeah. So if you understand your point, there is unconscious process, which are basically like reflexes, in which you have these shortcuts that you go directly from the sensory to the motor pathway, bypassing any sort of conscious perception. Consciousness is such a complex topic for neuroscience and abuse topic for neuroscience that I don't have a strong opinion on it. I really am agnostic to the fact that we really did not came down to boil down a definition for consciousness. There is a group in France that is based consciousness on the ability to report having perceived something, and is trying to make like sort of let's say neural basis of consciousness in the time that you react to create the pattern of neural activity that is associated to that particular stimulus. Seems to be 300 milliseconds, if you want to know. This is Stanislas Dehaene. he's great, and is definitely an important topic. It was an important topic probably for the last couple of 20 years, the graal of neuroscience. Now people are sort of moving on, looking for neural correlates of consciousness. They seems to be there in different parts of the brain. But being able to distinguish consciousness for unconsciousness and what you said, laughter, to coordinate motor output is actually really an important function of the brain, right? You need to make a mental image of what you do, Fabio. You need to create a memory of what you do, David, and you need to use this memory to create action. It's the same triad that we followed yesterday. Do you see the slide? No, right? Okay. This is great. But you see them now. All right, so I just want to go fast for this. We have talked about this to understand how to control our body, to perceive the world around us, to make associations. This is one thing that that we study a lot in the lab. So of course we don't study it with pizza, but we study with other stimuli, and it's something that is going to be the topic of tomorrow and on Thursday's lecture. So just keep it in mind, and to create memories and learn from our own experiences. There was a moment in which we really thought that we could not understand how the brain works and how the brain does this stuff. And the reason, and it wasn't too far in time, it was the mid of the 50s, right? In which people like Pavlov, Skinner, and Watson were basically not the same Watson as the Watson and Crick pair. They were saying that, you know, our brain is sort of a black box that sits somehow between perception and action. And because you cannot really see the brain in action, you cannot really probe the brain in action, you're not going to be able to understand how it works. And in particular, Pavlov, you might have heard about it, developed some sort of tools that he could do with animals to actually investigate the effect of this black box on the creation of perception, but without really like tapping into how this could happen, right? Because he thought philosophically that this was not accessible. I just want to refresh your mind, because this is a concept that you will see on Thursday with Wilde and with her fear conditioning experiment. Then you can condition an animal to explicitly elicit a behavioral response to a neutral stimulus by pairing that neutral stimulus to a stimulus that is meaningful for them. What I mean is that you know that before the conditioning, the animal sees food and it starts salivating. But also before conditioning, it doesn't do anything particular when a bell is rung. But if during the conditioning you start to pair the bell with food induce salivation, and by training, also the ring of the bell is going to induce salivation in the animal. So the brain has created an association between a neutral stimulus and a conditioning stimulus to give basically like a response. Okay, but the behavior did not say that the brain didn't do anything. It said that we cannot study, and it said that we cannot understand it because we don't have the means to go deep into the brain. Always in the 50s, those, and the end of the 50s, there were other people like Chomsky, Minsky, and Neisser, who instead decided that maybe we can actually really open this black box. And they started to coin the term cognition to define what the brain is actually doing in between perception and action, right? That is perceiving the world around us, processing the sensory information that we give it, and transform it, elaborate it, store it, recover it, and use it. It's basically like use the information that you acquire through the senses to create new information, and then direct your behavior based on that information. So how does it do it? They of course didn't explain it. They were sort of philosophers at that time, but they said that we can actually achieve it, and we can actually achieve understanding information, how the brain perceives, creates, and processes information by looking at what the brain does. So once we boil down the fact that the brain is a device that creates, processes, and stores information, can you name another one that does the same? Come on, it's not difficult. You're stating it right now, and it's not me.
Computer.
Perfect. Yes, a computer. And in fact, the analogy that your brain is a computer, the brain is really computing stuff and so on, I put it here because it's a very large analogy that has been used in the field, that has been questioned a lot right now with the rise of artificial intelligence, to say, you know, I mean, the brain and a computer don't really work in the same way, so you cannot really make the analogy. I just want you to take this as a point that, you know, in the same way that the brain is able to change the value of 1 and 0 that it basically stores in the bit, the brain is also able to use the weight of different entities in the brain and store and process information by changing somehow the message that individual neurons communicate with each other in the way in which they talk to each other, right? If you think about the neuron as the individual computational component of the brain, then the way in which they talk to each other can be modulated by experience, which means that the brain needs to be plastic. If the brain wasn't plastic, and once you basically set a network architecture by combining all the different connectivity motifs that you have done before in a specific way, and these would be static from the beginning of your life to the end of your life, you could not do all the things that you have said before, like creating memory, visiting consciousness, divide what is conscious from what is unconscious, and use these to make your decision. So how does the brain stores and create information? We go back again to the 50s, and we in particular to a book that was published in 1949 by Donald Hebb, which again, it was theorizing that if the action of a cell A was near enough or could induce the excitation of cell B repeatedly and persistently, so that there was a repeat and persistent process by which cell A was firing cell B, some growth or metabolic process between cell A and cell B could actually take part in one or the other or both of these cells, so that the efficiency of A to induce the firing of B was increased. This is probably one of the most known quotes in neuroscience. It's one of the most important quotes in neuroscience that anticipated the discovery of the way in which synapses are actually modified by experience by at least 20, 30 years. In fact, this is been discovered only later on during the 70s, in which basically, like, by looking at the way in which synapses can change in response to the experience, we have discovered the phenomenon of LTP. What is LTP is basically what Hebb predicted. So when you have a cell A which induces the activity of cell B, the efficiency by which cell A communicates to cell B changes over time because of the growth of a metabolic process. In this case, would be like addition of receptors to the synapse, making the synapse stronger and so on. So that at the beginning of this process of long-term potentiation, you have the activity of cell A and cell B induce a small blip in the membrane potential, as we saw yesterday. The magnitude, so the amplitude of this blip, would become larger and larger as the synapse between A and B is increased. This is one way in which you can change the way in which neurons talk to each other, and which you can highlight the importance of having cell A firing on cell B. At the same time, there is the opposite process. That is, if A and B are, and we'll see later how, but if the message that A gives to B is not extremely important for the process of activity of B, the amplitude of this EPSP that A induces on B can decrease over time by a phenomenon that is called long-term potentiation. Okay, so in order for storing, processing information, representing, and use it to create memories and whatever, you need to be able to change the way in which neurons talk to each other, and you need to change the timing of the way in which they talk to each other for the way in which we were going to see in a moment. Let's go back to the big ideas that come from Donald Hebb intuition and quote, right? The first big idea is that synapses are plastic and they can be modified by their use. So if two neurons are repeatedly active, especially one before the other, the presynaptic before the postsynaptic, it probably means that what these neurons tell to each other is quite important, and that should be made stronger. What stronger means? It means that you increase a larger depolarization. A larger depolarization gets you closer to the threshold for the action potential, which means that the firing and action potential will be easier, and the efficiency by which neuron A is able to activate neuron B will be increased. At the same time, by strengthening the synapse between neuron A and neuron B, you have encoded some information already. And the information that you have encoded is that at a certain point, neuron A and neuron B were coactive. This is an important point. It's going to be coming back tomorrow and the day after. But the idea that you strengthen neurons at a certain point in time where active together is basically one of the processes by which you create memories. So I hope that this is quite clear between you. If it is not clear among you, just please let me know, because this is something that we're going to revisit tomorrow, and we're going to revisit on Thursday, especially when we're going to talk about the engram. Okay, how do you decide if you want to increase or decrease the efficiency of communication between two neurons? If you want to use LTP and LTD, by the timing of their activity. So if neuron A is active before neuron B, in other words, if the input neuron spikes before the output spikes, it means that the probability that the neuron A has said something to neuron B that has induced neuron B to fire a spike is very high. And that synapse is going to be paired and is going to be amplified. Before the pairing, you see there is a very small amplitude of the EPSP. After the pairing, the amplitude of the EPSP is done, right? On the other hand, if the input spikes arrives after the output spikes, namely B has already given his spikes when A gives his spikes, then most likely A has not taken part into firing neuron B, but neuron B was fired by another neuron, which means that the synapse between A and B is not extremely important from the point of view of firing neuron B, which is the aim. So the synapse gets depotentiated, and you see it here. So the amplitude of the EPSP is decreased on the occurrence after the pairing of neuron A and neuron B. All right, if you want to do this in a very systematic way, you can actually calculate precisely the time at which the neuron A spikes must be given in relation to the neuron B spikes. And you can see that you get LTP when A fires before B, and you get LTD when A fires after B. Okay, this is really what we talk about when we talk about timing of spikes being able to induce plasticity in the connectivity between a neuron A and a neuron B. That goes into the larger umbrella of what we define as spiking time dependent plasticity. The other thing related to EBS that I wanted to tell you is that the growth and the adduction of LTP can not only potentiate one synapse, the synapse that is already there, but can even induce the formation of a new synapse, which will strengthen additionally the importance of neuron A into firing neuron B, and will highlight that the message that neuron A conveys to neuron B will be actually more very, very important. So in the end, we come to the realization that not all the synapses are equally effective in depolarizing the synaptic output. By itself, we are not talking about some dendritic integration. In this case, we're not talking about summation or temporal or spatial summation. We have some synapses that are potentiated and will induce a larger depolarization, and some synapses that are depotentiated and will induce a smaller depolarization. Okay? And each synapse will have a different weight, meaning that a different efficiency in depolarizing the postsynaptic neuron. This weight can be changed by experience and is one of the ways in which information is encoded into the brain. In this particular case, going back to the one before, that at a certain point in time, neuron A was active immediately before neuron B. Okay? All this concept of potentiation, of coactivity, and of different weights of synapses, keep it in mind, because it's going to be really important in the way in which we talk tomorrow about creating information, storing information, and recreating systems that can do cognitive or can reproduce cognitive function in silico. Okay, the second big idea that came from Donald Hebb was that if two neurons are repeatedly firing together, they will form a specific neuronal ensemble that can encode a specific stimulus. Meaning if two neurons are active together means that their connection gets stronger and stronger with each other. And in the end, they're gonna be basically like co-active in instances of reproduction of the stimulus. This is a general principle in the brain. Very rarely in higher vertebrate, at least, information is encoded in each individual neuron. Usually when we talk about multiple neurons are co-active together to encode for the same stimulus, for the same memory, and for the same action. And in this way, the concept of neuronal ensemble that Donald Hebb was foreshadowing in the 1949 is the basis of a very important field of neuroscience research during the past 5-10 years, which is the search of the physical traces of memories, which people have been called the engram. The intuition was that when you're doing some experience, the group of neurons that were coactive during that experience are going to be strengthening connectivity with each other in order to create a neuronal ensemble or an engram that is able to encode for that specific experience in your brain. So that when you reactivate that specific neuronal ensemble, you can recall the information about their formation, meaning their memory. We're going to talk about these on Thursday, so just keep your hold in mind. But there are two important things that stem from the idea of synaptic plasticity and the idea that controlling when spikes happen in a neuron is extremely important to create and select which synapses can be potentiated and which synapses can be depotentiated. So how do we tie it together to what we have discussed this morning about connectivity motifs? Here you see really the big power of connectivity motifs. I've told you that connectivity motifs decide in last instance the timing of the spike of the output neuron or the neuron in the network in general. By building together network architecture that are composed by multiple connectivity motifs at the same time, you can regulate which neurons are active and when. And if the two neurons are active according to the principle of synaptic plasticity that we have seen before, so one before the other, you can decide which synapses are going to be strengthened and which synapses are going to be weakened in order to form neuronal ensembles that become the unit, the substrate on which you actually encode information. So you go all the way from the network to synaptic plasticity and from synaptic plasticity to the biological basis of memory just by controlling the timing in which neuronal excitation happens, which is an extremely important thing that gets regulated in the brain. And one thing that you're going to explore this afternoon with your practical exercise, in which you're going to build network architectures that are composed of the connectivity motifs that we have seen this morning. Any question? Have you already worked your way through LTP and LTD during your course? So these are concepts that are really familiar to you. The way in which you basically build memories based on this is something extremely fascinating to studies, and in which you use it like to create network architecture that give rise to very complex things that the brain does. It's something that we're going to see tomorrow. But I think the main idea that you should really take on, the take-home message that you should really bring home today is that you really need to regulate the temporal profile of activity of the neuron, because a lot of information can be stored in this temporal profile, and this can become the basis for selecting which neurons communication, if you want, you need to potentiate, you can potentiate, and which one instead you want to depotentiate and maybe get rid of with long-term depression.
One question.
Yeah.
What can lead to long-term depression and what can lead to long-term potentiation? I mean, if we learn something, we have a change in synaptic plasticity. Yeah, and what can cause long-term potentiation and LTP?
You mean the stimulus or the pathways?
Stimulus.
Okay, so the stimulus is, for example, you have the two neurons which have been selected because they are active at the same time according to the rule that you see before. Let's take back the example of CA3. I'll go back to the network there. So wait 1 second. You see my screen now, right? So think about these synapses, right? So these synapses with each other are active with the proper temporal delay that is defined by sensory potentiation by, for example, being in a certain position of the environment or being in a certain location. You will see that CA3 as a sort of an ambivalent role, if you want. It can be driven It can be thought of as a place where you create maps of the environment around you, but it's also a place in which you use this information to create memories, right? So the stimulus that can create this long-term potentiation at the synapse is actually the type of stimulus that CA3 cares about. So there is not one specific stimulus that I tell you this has created long-term potentiation. It's more of the same type of device that you see over and over again in different parts of the brain that is used to strengthen the information between two neurons, whatever that information is. If you're looking at the motor cortex, for example, you can induce LTP by learning a specific motor routine. If you're looking at the cerebellum, you can learn LTP by doing a task in which you learn to be dexterous. So basically like to walk on a beam, for example, right? When you tend your cord through two cables. So in the end, it's not one specific stimulus that induces LTP. The stimulus that induces LTP depends on the area that you're looking at. LTP is given by the coactivity of these two neurons. So the correlation that you find between the two, it's a little bit depending on where you actually are looking at. I don't know if I made myself clear, if this was the question that you were asking, right?
Yes.
Okay.
I also have a minor question, it's just out of
Yeah.
curiosity. Do substances that are commonly abused also affect the long-term potentiation in depression?
Yes, this is a great question because this is actually what happens. And that's the same thing that I was mentioning before to David. They do in specific areas of the brain. So for example, there are different subcortical areas that take care, for example, of mediating release of certain type of neurotransmitters that we are really not going to go into details during the blog course. But it is more and more clear that like in addicted people, the administration of substances like alcohol, cannabinoids, or other type of drugs like cocaine and so on, can increase plasticity in this area or can inhibit plasticity in this area. And that will basically like lead these people to have more and more craving or, to create a biological type of addiction. When you talk about addiction, you always talk about two terms. One is the psychological and the other one is the biological. LTP is involved in some sort of biological type of addiction, yeah, in this specific area of the subcortical part of the brain.
Okay, thanks.
Yeah, no problem. Any more questions before we break for lunch? All right, so I guess we're going to see each other, each one in his individual group at 12:30, right? So that we have enough time to play around with your exercises. Cool. See you later.